Hello, these are notes 7.3 for geometry covering similar triangles and proving that two triangles are similar. So there are three ways that we're going to show how to prove that two different triangles are similar. The first way, called our angle-angle similarity, or AA similarity. And this is a theorem that goes like this. It says if two angles of one triangle are congruent to two angles from the other triangle, then the two triangles are similar. Okay. You'll notice that this is different than our congruent triangle theorems, where we had our side, 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 for example, or side angle side. This is different because we add the little symbol, the similarity symbol behind those to help distinguish so that we don't think that this is a congruence to the triangle. So again, this is just for similar. Let's take a look at this triangle and be specific to this angle with this triangle. Let's say this is ABC, and we're trying to show that ABC is similar to triangle DEF. By the angle-angle similarity postulate, what we would do is we would look at these two and we would say angle A is similar, or excuse me, angle A is congruent to angle D. And if we also show that angle B is congruent to angle E, we have two triangles from the larger triangle that are congruent to two triangles from the smaller triangle. Therefore, these two triangles are congruent, A, B, C. I said congruent, I apologize for that. These two triangles are similar. And we would say by the angle-angle similarity theorem. Let's take a look at the next way that we show the two triangles are similar. And this one is called the side-side-side similarity. Again, you'll see, like we said in this one, we add the similarity symbol behind this to distinguish between congruence and similarity. And what does this one say? This one says all sides of one triangle are proportional to corresponding sides from the other triangle, then the two triangles are similar. And this was covered in our first sections in this chapter, and that was the idea of setting up a proportion where two fractions are going to be equal to each other. So when we do a side-side-side similarity postulate, we're going to see a bunch of proportions. And specifically, let's take a look at this triangle again, and we'll just go A, B, C, and D, E, F. And to show that these are similar by the side, we'll start by comparing these two sides here. We'll say AB is to DE, big triangle to small triangle, as our next set of sides would be BC is to EF. And of course, if this proves to be equal to each other, in other words, if we checked our cross products here, BC and DE multiplied together, and AB and EF multiplied those two together and got the same cross products, then we would say that these two are proportional as long as those two are equal. Now, this is one set of sides. We also need to compare that with the last set of sides. So we could compare again each one of these. And we need to take a look at this last one over here, and that would be comparing AB to DF. If we write that ratio and compare that to, let's say, BC is to EF, we would multiply AB times EF, BC times DF. F didn't turn out very well. And the result would be proving that these are similar if those two cross products were equal to each other. And just like we did last time, then we would say that triangle ABC is similar to, that's our similar symbol, not our congruent or equal to, DEF. But of course, this time it would be by our side similarity. Our last one also looks like one of our congruent theorems, and that's our side angle side similarity. And it goes like this. If two sides of one triangle are proportional to two sides from the other triangle, and the included angles are congruent, then the triangles are similar. You can see this one shares both properties here, except this one's only looking at one set of angles, where this one looked at two, and this one's only comparing two of the three sides, not all three sides. Okay. And I want to emphasize to you that this is not any angle, it has to be the included angle. The same idea that we had when we were looking at the side angle side congruence, that we had to make sure that we were talking about the angle that was in between. Let's take a look then at how this one will work. And it's going to look something like this. We'll again be comparing these two triangles, ABC and DEF. We want to go ahead and start out with the proportional sides. We can look at AB and compare that to the length of DE. And then take a look at, say, side BC and compare that to side EF. If these two cross products prove to be the same value, then we know that those two are proportional to each other. And then we have to look at the included angle. Same idea we had with our congruence triangles. It has to be the angle that's in between. Included means in between. The angle that's made by the two sides that we showed that are proportional. It could not be angle A and D and C and E. It only can be that angle B is congruent to angle E in this case, because that's the included angle between them. Once we have these two things said, then we know that triangle ABC is similar to triangle DEF, this time by our side angle side similarity postulate. Okay, so those are the three. Let's take a look at a few triangles and determine if they are indeed similar. If so, we'll write a similarity statement. Similarity statement is what we wrote in each one of these lines up above. And we'll explain, or we'll name the postulate or theorem that we have up above, either the angle, the side angle side, or the side side similarity postulates or theorems. Okay. And when we look at our first one, I think all of us can quickly recognize that we do have a pair of angles that are congruent, because our good old friend, our vertical angles, has shown up again. And that is that angle AXB, the one on the left, is congruent to angle CXD. So we've got one angle Not sure anything about the other two angles, so that kind of eliminates our angle-angle similarity postulate. So let's go ahead and compare the sides. We're going to compare 6 from the triangle on the left to 9. 6 is smaller than 8, 9 is smaller than 12. So those are the two that I'm going to group together if it doesn't show me clearly which ones correspond. So we're going to compare 6 is to 9 as 8 is to 12. This gives us two sets of numbers that will multiply to get the cross products. The cross product of 6 times 12 gives us 72. The cross product of 9 times 8 also gives us 72. Since those are the same, we know that, are these similar? Yes, indeed. These two triangles are similar. So let's do part B on this, and let's go ahead and write the similarity statement. And the similarity statement will be triangle AXB, the smaller one on the left, is similar to triangle CXD, the larger one on the right. And the reason we know that this is true is this is by our side angle side. The angle is between the two sides. Therefore, this is our side angle side similarity postulate. Let's go ahead and take a look at the next one. And the next one, again, our good old friend vertical angles appears again. And this, we know that angle AXB is congruent to angle CXD. And as a matter of fact, we also have the exact same proportion we had last time. We see that 6 is to 9 as 8 is to 12. I'm comparing the one on the left, the smaller one, to the one that's on the right. And the result will give us the same cross products of 72. So those check out. Now, some of you may have already noticed and trying to tell me, stop, wait a second, no need to do this, because we do have a dilemma here. We do show that two pairs of sides are congruent or proportional. We don't know anything about this third side, nor do we know anything about the other two pairs of angles. Therefore, we can't get this by side, 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 or angle, angle. And since these two angles are not in between the two sides that are proportional, we can't also do this one by the side, angle, side. None of those are possible. Therefore, this one is not possible. In other words, there's not enough information for us to know whether they are similar or not. Again, the distinguishing between these two are the location of the angles. Let's go ahead and take a look at C. And right away, our good buddy, vertical angles show up. So from the start, we know that angle MRT must be congruent to angle XRW. That's a nice way to start. We've got one angle. Looking around, I don't see any measurements of the sides. I also don't see anything that says congruent to or a midpoint or something like that. So we don't know anything about the sides. We're going to have to get another angle to get our angle, or this one's going to be a not possible. Fortunately for us, we remember back to the chapter that had our parallel lines cut by a transversal. I'll look at this one as the transversal going from T to W. And in this, you'll see that we have angle T and angle W have to be congruent if these two lines are indeed parallel. And the reason we know this is because these are alternate interior angles. They're between the two lines that we've highlighted in pink, and one's on this upper left and lower right. Therefore, they are alternate interior angles and must be congruent. And now we know for sure that triangle MRT must be similar to XRW. And be specific with the arrangement here, because we have to have corresponding angles between the R and the R in the middle, and also T and W. Notice I put T at the end here, so W has to be at the end on the next one. And the reason we know this is by our angle-angle similarity. Let's take a look at our next one. 4 times in a row, our good old friend vertical angles have shown up. So in the last one, or in this present one that we have DUE is congruent to TUS. And we have some sides to compare here. So let's go ahead and take a look at these two guys here and compare 39 is to 16 as, it's supposed to be a 6, as 40 is to 16. I've compared the larger triangle to the smaller triangle, and I think that this one's pretty obvious for us to see. If we take 40 and divide it by 16 and 39 divided by 16, we won't get the same number. So there's no way that these two are proportional. If you don't believe me, we can easily check our cross products, and that would give us 39 times 16 is 624. Whereas 16 times 40 is 640. Neither of these are congruent. Therefore, we know that this is definitely not similar. And we know that because the sides are not proportional. Definitely not. Let's take a look at the next one. In this one, we have no vertical angles. This appears to be a right angle, but we don't know for sure. So I'm looking at this and I don't know anything about the angles. So let's go ahead and compare the sides. I'm going to compare the one on the left, the larger triangle, to the one on the right. I'm going to choose the largest value here of 84 and look at these three numbers and choose to compare that with the largest one over here. So I'll write the proportion 84 is to 14. And then just to give myself an order or a plan of attack, I'm going to go with the next largest number, 72, find the largest between these. 12 is definitely larger than 8, and compare those two. So this would be 72 is to 12. Okay. And then what we're going to do is a quick little cross product here, 14 and 72. And 84 and 12. We need to multiply these together to check and see what we get. And when we multiply 84 times 12, we get a, check my numbers here, sorry, 84 times 12. Yep, indeed. That gives us 1008. And then if we put in 14 times 72 in our calculator, we'll also get 1008. Therefore, this checks out. Now we have to be sure that we don't stop here. We have another set of angles that we need to verify, or excuse me, sides that we need to verify are proportional. We need to check 48 is to 8. And I'm going to choose the 72 is 212. I could have easily chosen the other one, doesn't matter. But we're going to do our cross products. 48 times 12 gives us 576. 8 times 72, believe it or not, also gives us 576. Since both of those are equal to each other, we know that both of these proportions are true. Therefore, triangle ABC on the left has to be similar to triangle HGF on the right, and we know this by the side similarity postulate. Let's take a look at our last one. And in this one, we do have two triangles here. One of them is the one that's down here on the lower left, and then the other one is the outside lines of this, the large triangle. So we're going to compare these and check and see if they are indeed similar. Yeah. Now, in this one, you may not see it right away, but we actually have our reflexive property showing up. Our reflexive property, if you recall, RST is as easy as 1, 2, 3. Our reflexive property is when we have something congruent to itself. And you'll see in both of these triangles, this angle here is angle K. So in the smaller triangle, we have angle K. In the larger angle, we also have angle K. And angle K must be congruent to itself by the reflexive property. So we start off with two angles congruent. Now let's go ahead and compare the sides. In the smaller triangle, you'll see we have a side here, KB, that is 16. We'll compare 16 to this side in the larger triangle, K to L, which is 88. 16 is to 88 as, let's look in the next triangle, and that is 25 is to, oh, wait a second here. This 107, it doesn't show us this being the total length from here to here. This is shown up here between C and M. So in order to get the total length of this side, we need to add the 107 and the 25. That gives us a 132 for this. So 25 is to 132. And again, we can do our cross products here to check and see if these are proportional. We can take 16 times 32, and we can take 25 times 88 and compare them. 16 times 32 gives us 2,112. 88 times 25 gives us 2,200. These are not equal, therefore these are not proportional. Now I do want to show you another way that this also could be done. Rather than our cross products, using Desmos in a quite easy way. And get these back off there and put those back in. So one thing you can do is you can enter in 16 divided by 18, that fraction, and you'll see that that gives us this decimal of 0.18181818. Also, you'll see that there's a little fraction symbol over here that if we press that, your answer is going to change to a simplified fraction, which tells us that this left hand, our 1688s, would simplify to the fraction 2/11ths, which again equaled 0.181818 repeating. Now let's compare that to the fraction we had on the other side, and that was 25 divided by 132. That gives us a fraction that's pretty close. The 25 divided by 132 gives us as a decimal 0.018, 939393. So it's close, but not exact. And as a matter of fact, if I click this over here and it reduces it or simplifies the fraction, you'll see that this is a simplified fraction, and the fractions aren't equal to each other. When these are simplified, both of these have to be the exact same amount as a fraction when they're simplified. If not, then they are not proportional to each other. So again, since both of these didn't simplify to the same fraction, nor did they give us the same decimal, we also know that they're not proportional. So in each one of these over here, if you want to, you can just enter this fraction into your Desmos and this one into your Desmos, and then just compare those two numbers to see if they are equal. Unless it specifically asks you to do your cross products, you can do either one of those methods as you can. Okay? And again, these are not similar because the sides were not proportional. Now, let's use these similar triangles to go ahead and find some links, missing links in the similar triangles. So this problem starts out by saying the triangles are similar. We don't have to go through the steps that we did on the last one to show that they are similar. We know from the beginning that they are. So let's go ahead and solve for x. You can pretty quickly see that we're going to compare x to 11. X is to 11, and now we have a choice between the 15 and the 12, or 15 and 10. And I'm just going to go ahead and choose the 15 and compare that to not 8. 15 and 10 from this triangle. 15 is larger than 10. So if these two indeed are similar, I cannot pair 15 to the smaller of these two numbers. I have to pair this with the larger of the two numbers. Very common mistake is for people to just compare the number that is closest to it. If I choose the larger of these two numbers, 15, it has to be corresponding to the larger of the two on the other side. Okay. Our cross products here will give us an 12x, and 11 times 15 is 165. Once we get to this, you'll see that we're just going to divide both sides by 12, and x will equal, in this case, 13.75. Let's take a look at our next one. In this one, we have two similar triangles. One is the outside triangle, and the other one is the smaller one that's on the inside. Just like our last one, these two are pretty straightforward to match up, that we're going to compare x is to 17 as, remember, this is the whole side of the larger triangle. We have to pair that to the whole side, or use the whole side of this triangle and compare that to the corresponding small side. So even though we have in here the numbers or number 8 here, that is not the total length of this big triangle. That big triangle is 8 plus 12 on this right-hand side, this being x, and then our third side is over here. Okay. So that would mean that we're going to compare 8 plus 12, or 20, from the large triangle to 12 from the smaller triangle. Let's do our cross products here. And this will give us 12x equals 340. When we divide both sides by 12, we get 28.333 repeating. This one also could have been done by comparing the x is to 17 to the numbers that are on the right side. Like we did on the left side, we need to compare the total length, 15 plus 10 or 25, to just this length here of 15. And do some cross products here. This will give us 15x. 17 times 25 will be 425. 425 divided by 15 also gets 28.33. So I just wanted to show you that if we're given more numbers, it doesn't matter which one you choose. Just make sure, again, you're comparing the big triangle to the small triangle. And it has to be the total length in the big triangle, not just a part of that. Let's take a look at our last one. And in this one, we're going to compare x and 12. So x is to 12 as 42 is to 14. Just ran over my other numbers there. Apologize for that. Let's do some cross products. X times 14 gives us 14x. 12 times 42 gives us 504. 504 divided by 14 gives us 36 for our missing one. Next one is a very common problem that you'll find in every single website, every single textbook that has proportional triangles in it, because this is a way that for millennium upon millennium that humans have used shadows to measure lengths. Okay? And it goes like this. You have a person who is 6 foot tall, and at a certain time, that person cast a shadow along the ground of 18 feet. This assumes you know how shadows work, that if you stand there, the shadow is going to go out in front of you. And if we connect the top of our head to the end of our shadow, you'll see that we have a triangle. And as a matter of fact, it's a right triangle because we measure height perpendicular to the ground, and shadows are going to be along a flat surface like this. Then at the exact same time over here, we notice that we have this tree that also casts a shadow that's not this time, or that is 93 feet long. We don't know what the height of that tree is. We can make that X or Y or H for height. And since the sun is so far away, the angle that's created between the ground and the sun in our shadow and the angle between the height of the tree and the shadow, those angles are going to be the exact same because, again, the sun is so far away. And of course, we have two right angles there. All right angles are congruent. So these two triangles are similar by angle-angle similarity postulate. And since they are similar, we can go ahead and write the proportion. And that proportion would be 6 is to x, our height and the tree's height, or this 6 foot person's height, and then compare that to that person's shadow of 18 and the length of the tree's shadow of 93. Quick little cross products. Or if you remember back from middle school, we even use the word cross multiply and divide. Cross multiply would be the 6 times 93. The divide would be dividing by 18. In middle school, when we did that, we were actually doing two algebra steps in basically one problem on our calculator. We multiplied the cross products, and then to solve for x, we divided by 18. The result is going to give us, in this case, a tree or an X value that's 31 feet tall. A 31-foot tall tree will cast a shadow of 93 feet. At the same time, a 6-foot tall person casts a shadow of 18 feet. Nice little word problem that, again, you should kind of expect this. This does show up on a ton of standardized tests too. And again, very, very common problem. Now we've got 3 proofs that we can use, or we can complete using our similarity postulates and statements or on theorems. So let's go ahead and start this guy off. We can see that the first line is blank. That by now is super, 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 super easy for us. We just look up here to what is given. And if it's a computer, we're going to click on it and drag it down. Since I don't have that capability, I'll have to use my writing instruments. And that is that MX is perpendicular to AB, and the measure of angle A equals the measure of angle B, which are both 58 degrees. Why do I know that? Because it is given. And in this particular problem, I have 2 different statements written in the same given line. That is okay, but not always used. Usually if they're 2 different statements, they're in different lines. Or I won't say usually, but many times you'll also find that these are written in 2 different lines. Whatever is available for you, there is no absolute rule that you have to put 2 different statements on 2 different lines, or that you have to put all your givens in 1 line. But in this case, like we said, we're putting it into 1 line. And then a very common thing, we see a symbol here. Whenever we see a symbol and a word in one statement, then the definition of that symbol or word shows up in the next line or one after that. And we know since MX is perpendicular to AB, let's look over here. MX is perpendicular to AB. We know that we have a set of right angles here. The first one being angle MXA. MXA, and the other one is angle BXK or KXB. I don't care which one you do, but BXK are, running out of room here, right angles. Wrote a little bit too big there. Okay. This is not part of line number 3. That is line number 2. And then we can stick in here line number 3, and that is that angle MXA is congruent to angle BXK, because all right angles are indeed congruent. Now you can see that in our given statement, we had angle A congruent to angle B, and now we have these 2 right angles congruent to each other. Therefore, we can conclude what we're asked to prove, and that is that triangle AXM is I put congruent, sorry about that, is similar to triangle BXK, and the reason we know this is because of the angle-angle similarity statement or postulate. Let's go ahead and take a look at our next one. And the next one, it starts us off with the given statement. Put that one in here. That these 2 lines over here, the line through K and H and the line through J and I, are indeed parallel to each other. In the next line, they start out by saying angle J. So let's go over to our diagram and look for angle J. It's down here in the lower left-hand corner. And it says it must be similar to, and I think you can easily see that this is going to be angle, and we're going to need to use 3 letters on this, not just say K, because we want to make sure we're using the correct angle here, and that is GKH. We know that because these two angles are corresponding angles. And next, it makes the statement, or at least starts the statement, that angle I is congruent to. An easy observation would show us that this is congruent to angle GHK, because those are also corresponding angles. And we know when two lines are parallel, they're cut by a transversal, the corresponding angles must be congruent by our corresponding angle theorem. Now we have two triangles, the smaller one that's up above, and then the outer sides of this, the larger one, that have two angles that are congruent. And now we can make the conclusion, step number 4, that triangle JGI is similar to triangle KGH by the angle similarity postulate. All done. Let's take a look at this next one. And in the next one, they start off by writing a proportion. Let's see what that proportion looks like over here in our diagram. It's saying if we compare MN to PR and we compare ON to QR, those two are proportional. That is part of our given statement. And then another part of the given statement, this time written on a second line, is that these two angles here, N and R, are congruent to each other. And this one's a pretty easy proof because the two given statements are all we need to show that these two triangles are congruent. And the reason that we know that those are congruent is because of the side angle side similarity. The two sides that make up this angle, the included angle, are proportional, and the two included angles are congruent. Therefore, these are similar by side angle side. I hope you've enjoyed these notes. If you have any questions on those, feel free to go back and take a look at those or ask me face to face when we get time.